Okay, it's 3:40 and it's time to start our lecture. Hopefully you can hear me. The audio is okay. If it is, can you say so in the chat? That way I know that for sure that you can hear me. Otherwise, I gotta go track down a bug. Okay, perfect. Hello, Miguel, Mitchell, Sarah. It's good to see everyone here. I see at least there's people watching, so it's not just going to be me talking to myself for the next 2 hours. So we're going to do lecture 2. And this is a bit of a review and some basic algebra. And while I was putting this lecture together, I also feel that we can also review some of the number systems as well. And also, why are they here in the first place? And the textbooks goes through this. So there's kind of, we'll get into lots of different things. We'll talk about discrete versus continuous, things that are countable. So, when we started out as humans, even birds or other animals have a concept of counting, and we start off with the natural numbers. We have 1, 2, 3, 4, so on and so forth. The dots mean that so on and so forth. This is set notation, and we covered this in 106. So these are the natural numbers. And we call them natural numbers because they're natural. We find them in nature, and it seems that counting is an innate ability. Okay. The next kind of leap forward in terms of number systems is we got the concept of zero, that we can actually have nothing. This shows that there's some sort of quantity, but to show that there's nothing, we came up with the idea of zero. Some people think of it as a placeholder, but it's quite a leap forward from just counting things to actually having nothing. And so using this notation, I could say that basically the whole numbers here are really just that we've taken the natural numbers and we've added or union with the idea of zero. Now what's nice about these is we can do addition and we can do multiplication, and we never leave these number systems. And usually we call that in mathematics that it's closed. It's closed under operation. For example, if I did 3 plus 4, well, that's 7. And that's still an element of the natural numbers. It hasn't left its number system. It hasn't gone outside. It's not outside of its set. Same thing with the whole numbers. If I multiply by 0 by 7, that's equal to 0. And again, that's still an element of itself. So again, I can have natural numbers here, and I'm staying inside of here. This is for the addition. I can multiply or addition, it doesn't matter. In these two sets, I'm still staying within the same set. Perfect. Why is this still limiting? Is because I don't allow for the idea of subtraction. What happens with subtraction? Well, for instance, I could have a number, say 3 minus 4, and using modern notation, because if we had only the natural and the whole numbers, I wouldn't be able to give you an answer. This would be undefined. And we know we call this -1. So, in mathematics, we're always that nagging 3-year-old child, like, what if, or why is this, why are you doing this? What if we somehow, took away something? Well, those are the questions that we start asking ourselves. And so we had, what about subtraction? Okay, so our answer then for that was, okay, well, we'll allow negative numbers now into this system. So we took kind of the whole numbers, including 0, and then we allowed negative numbers. So we, allowed -3, and we allowed -2, -1, we allowed 0, 1, 2, 3, ... So we can let that go on forever in the right direction. We can let it go on forever in the left direction. We'll put our curly braces around it, call it a set. What are we going to call these? They called it the integers. So these are integers. Now, again, depending on who invented the mathematics, they get to name it. So they gave this Z, or Z for everyone else outside of the in the United States or elsewhere. And why did we call that Z? Well, okay, these are numbers. Or basically, this came from the German word Zahl, and it's German for number. Okay, so we've got kind of these natural counting numbers that we like. And I keep saying the word counting or countable. What does that mean? Well, in math, we actually, it's a very precise definition. And I'll give you a taste of it. So, here's a definition. So a set is countable if you can create what is called a 1-to-1 correspondence. And that's a 1-to-1 correspondence with the natural numbers. Okay. 1-to-1 correspondence may sound very technical, but it's simple to illustrate. We always seem to come up with very precise, technical words for very simple things in mathematics. And so, is, for instance, is the whole number is countable. So is W, we can actually show that it is countable. And how do we do that? Well, okay, so I take the natural numbers, I write 1, 2, 3, so on and so forth. And then I have the natural numbers. And I come up with a correspondence, meaning I basically match for each element in the natural numbers. I come up with an element in the whole numbers that I can write it with. So I, just start at 0 and 1, 2, so on and so forth. So I actually come up with this 1-to-1 correspondence. So, you could, going from N to W, the naturals, it would be X. Basically, we map it to X plus 1. Or if we want to go backwards, so if we had Y and we were going in the opposite direction from W to N, we're just taking away 1. So again, there it is, a 1-to-1 correspondence. Okay, so you're going, what about the, the playful nature of mathematics? Okay, you did W, that was pretty easy. Okay, try doing that for for the integers is, are the integers countable? And yes, they are. So I'll say that they are countable. I won't put it in a form of question. This isn't Jeopardy. So we have the natural numbers, and again, I kind of write out my list. 1, 2, 3, 4, 5. Make sure I don't go too far off the page so that you can still see what I'm doing. Let me just... Okay. So then the next thing I can do is I write out my integers. And I kind of write them in a particular way. What I'll do is I'll make sure that 1 is 0. And then for each of them after that, I'll just write down like 1. I'll make 2 copies. And I'll make this one positive, and I'll make this one negative, and I'll make this one negative. So now what I do... Oh, and I didn't line that up very well. So I still have a one-to-one correspondence. If you, again, were going to ask me a question of, oh, what's the formula for getting from n to z or vice versa? Okay, it's not as simple as this, but I mean, the way that we could do this is we can create a function, say for going from, as an example, from going from n to the integers. What I'll say is that if I had an element x and I wanted to go from n, so like I said, I'll do I'll do 0 if x is equal to 1. If I'll do x divided by 2 if x is even. Okay, and minus x minus 1 over 2 if x is greater than 1 is even, or sorry, odd. There we go. So again, that's just a formula that we can use for going back. Okay. So again, we've got lots of operations. We've covered addition, we've covered subtraction, we've covered multiplication. Okay. So, the next question is, and you already know it because we've been taught in this in school, what about division? Division. And probably I spelled that wrong. Anyways, if you don't know how to spell something, that's the nice thing about using a pen, you kind of mess it up a little bit and everyone is none the wiser. That's supposed to be division. Right. So we have something like 7 divided by 2. Well, again, there's no number in the integers that could give us that number. So again, it's not in the integers. So now we've got a number now that we don't know what to do with now. It's not in the integers. So now again, we create a new number system. We create a system that allows it to have rational numbers or fractional numbers, however you prefer to call it. But we usually call them rationals. And so this is a rational number. AKA a fraction. fractional number. And again, on the top here, we have special terminology for it. We have on the top, we call that the numerator. And then on the bottom, we call it the denominator. Okay. Okay, so we're going to create a new number system. We're going from the integers to the rationals. So we call it the set rationals, Q. And we will write it in set form. So we'll call it, we'll have two arbitrary numbers. We'll call them M and N, such that M is an element of the integers and N is an element of the integers. And I have one more condition, and because everyone will start typing it in the chat, which is the denominator cannot equal 0. Okay. So again, if I had something like 7/2 now, yes, now we're inside the quotients. Is it closed under division? Meaning that do I have every element in Q, if I divided it or I did something with it, would I still stay inside of Q? You know, and the answer is no. Because division by 0 is not defined. Okay? So no, it's not closed under division. We basically, we have to exclude this. So that's how we kind of make it, you know, how it works for us. Otherwise, we you know, it's just, you know, it's just not defined. Okay. Sure, you might ask me now, okay, oh yeah, and another question people might ask me is, why Q? This comes from the Italian for quotient. I wish I could remember how to spell Italian, but I can't. But it was from Italian for quotient. Okay, so are there other issues with it? Yes, because there's numbers in there that still we know about, and it's still not in there. So, you know, any issues or any other problems? And the answer is yes. And it's a big yes, because it comes even from ancient Greek times. So in ancient Greece, there were schools of philosophers, and at that time Pythagoras was a very big name in mathematics, and of course we all know him from his Pythagorean theorem. And again, he had an annoying student, as the legend goes. And he, you know, they came up with the Pythagoras theorem. They figured out what the length of the hypotenuse of a triangle is. And, you know, again, like an annoying mathematician or annoying student or annoying child, they go, okay, well, I have a triangle that has height of 1 and I have a base of 1. tell me, Pythagoras, what is the hypotenuse, the length of the hypotenuse? And Pythagoras was very upset because he believed that it should have been a ratio of integers. And legend has it, he then took his student and drowned him in the sea. We don't do that anymore. Mathematical education has come a long way from that time. We still get annoyed, but things have changed since the ancient Greeks. But we do know that from Pythagoras' theorem that 1 and 1 gives us the hypotenuse to be square root of 2. And, you know, a logical question somebody would ask, well, sure, maybe it's really, you know, is it rational? You know, come on, Pythagoras, is the square root of 2 rational? Not like it's sane or anything. It's just you know, following our definition. Can the square root of 2 be expressed as a ratio or a fraction of 2 integers? So that's a good question. And you know, this is how we start to prove things. You know, can I write as a rational? And that means then, like, can root 2, you know, be equal to some, you know, for some integer m, or, you know, okay, so again, these are questions. We're always asking ourselves questions, and we follow through with that. Let me just grab another piece of paper, because what we'll do is everyone is afraid of the word proof. I'm going to use this word, and that's it. Proof is a way of, you know, showing to somebody in a written form that something is true. You know, we can do a lot of hand waving. We can do a lot of you know, drawing of pictures or whatever. But in the end, we want to have a written argument for this. And so here's the proof. And it comes again from ancient times. This proof form is what we call by contradiction. Hopefully, if I taught 106 to you, you would have seen contradiction even in passing. But the idea behind it is that we assume something is true. We argue it to the point where we've arrived to a contradiction. Something doesn't make sense. And the only thing that we can say then about that is that the assumption that we made is wrong. So this is how we do it by contradiction. So we say, suppose, in order to derive a contradiction, that this is our big assumption, that the square root of 2 is rational. Okay, so what does that mean then? So then we can express square root of 2 as some fraction. So I say for some m, and again I'll put down that n cannot equal 0. So we're fine with that. The small little trick to this proof, again, every proof or argument that you'll see that's not trivial, there's always some little tidbit or something interesting about it. And the real part about this is that we'll say that we'll make an additional assumption that it's fine, we can do this. So we also assume that the fraction m over n is in reduced form. Okay? So again, not to put for like a reduced form, meaning like if I had a fraction, I had 3 over 9. That's not in reduced form. We want it in simplest form. So what we can actually do to this is we see that there is a common divisor between all of these. And the greatest common divisor of 3 and 9 is 3. So what I can do is I divide everything by 3 and I get it in what is called reduced form. So I divide by 3. So I'm dividing by 3. I divide by 3 here. So that leaves me with, when I do that, 1. And 9 divided by 3 gives me 3. So I'm left with 1 over 3. Okay, so I haven't done anything that's beyond what we've done in elementary school of greatest common divisor. So we also assume that m over n is in reduced form, and so that means, or mathematically, that the greatest common divisor of m and n is 1. So for instance, if I had two numbers, if I had a GCD, let's go 3 and 5, there is no common divisor. I was greatest common divisor or common denominator of 3 and 5. I can't divide anything by them. They're prime numbers, so there's nothing I can divide by them except for 1. So again, this is what we would call it reduced form. And that means that when we say reduced form, that the GCD is equal to 1. So that's fine. I can do this. This is an assumption that I know is true, and it's something that I don't have to worry about. It's this assumption that if I run into any problems, that this is going to be the issue. Okay. Does that require me? Okay, so this means m and n, do not share any factors except for 1. Okay. So I can carry on with a little bit of this. So I have square root of 2 is m over n. And then I will square both sides. So squaring both sides, Well, what I can do first is I'm going to bring this n over from the denominator. So I'll get square root of 2 times n is equal to m. So I just brought this over to the left-hand side, and I'm going to square them now. Okay. The idea now is that on this side here, if we use our exponent rules, I have x and y to the n. That is equal to x to the n times y to the n. So again, I can write square root of 2 squared n squared equals m squared. And so now I have 2n squared is equal to m squared. Okay, this is where we got to this point, and this is interesting. Because, like I said before, I said that m and n have no common divisors. But what is interesting about this is that m squared is equal to 2n squared. Which means that m squared is divisible by 2. Because it's inside of this. Because to get to m squared, it's just simply n squared times 2. It's divisible by 2. Okay, and you might be asking, okay, so what? Well, that means then that m squared is even. Okay, so what? It's not talking about m anymore. It kind of is. Because this means that m squared is equal to m times m. And the only way that m squared is even is if the m's themselves are even. So, again, m is even. Okay, so you're like, so what? M is even. Doesn't talk about, you know, you can have an even number, can you? Maybe. But the other thing that we need to worry about is, let me just rearrange this. So I have 2n squared is equal to m squared. I can write this as n squared is equal to m squared over 2. So again, we have to assume that this has to stay even. So what does this mean? Well, first of all, if I do that, I have an even number up top here, and I have an even number on the bottom. Which makes this is even. And again, by the same argument over here, if I have m squared, n is even as well. Okay, so that means that I have two even numbers. So m and n are even. So what? This is the contradiction. because for this means that since they're even, they have a common divisor, which is 2. So it means that it's not equal to 1, which then means that, you know, it breaks the GCD rule, which was okay. So that means then therefore square root of 2, which is our assumption that we started at the beginning, is not rational. Or in mathematical terms, we'll say that square root of 2 is not an element of the rational numbers. Okay, so again, so what? Let me just get this. It means that we have now a number system that still doesn't include numbers that are quite common for us, and we end up using the square root function. So we need to somehow include this, and this is how we get the reals. Second, let me just fix up my ordering of sheets. Okay. So then the question is how do we fix this? Well, we create a new number system that includes these not rationals. We'll call them irrationals. So we will say, you know, not rationals. Are equal to, you know, what we call irrationals. And what we do is we then take those plus the rationals and now we create a new set. And that is where we get the reals. So these are the real numbers. Okay. So let me just move that back up here. So we've done the real numbers. Why are these important? Like, how do we get this gap of we have irrationals and rationals. So for instance, I have, you know, square root of 2, and this is approximately equal to 1.41421356 ... And like we've said, okay, so there's irrationals and rationals. This is a irrational number. And what we can do is try to approximate it. And we can, since we know what the approximation is over on this side, we can actually come up with some fractions. So for instance, we can have like 14 over 10. These aren't very creative fractions, but let's say 141 over 100. We're getting closer. We have 1414 over 1,000, and so on and so forth. And you might be asking me, why are you telling me about this? Like, just hold tight. We're getting there. So what I'm saying is that we can get larger and larger fractions. We can get really close to the square root of 2. With rational numbers or fractions. But the point is, you will never get to touch it. Using the rational numbers, we can get closer and closer and closer, but you cannot touch it. Working only with the irrationals, or sorry, with the rationals. Okay. This idea, this very intuitive idea of getting really, really close to something, very close to what we call the limit. So you can get really close to something. So you know, this is kind of an intuitive way of thinking of it, but, you know, a limit is something you can get really close to, but cannot touch it. I've always made the joke that limits are like the museum or the artwork in a museum of the mathematical world. There's all these pretty things, you can look at them, but you can't touch them. You can get really close to it too, still can't touch it. So what we can say then is that square root of 2 is a limit point of Q. Okay, and this is quite technical at this point. We've talked about limits now, limit point of what am I going to get at is that this is the way that we can define something for the rationals. The rationals, or sorry, the reals. It's the set of all rationals along with the limit points of the rationals. Okay, so the question I should probably answer before I move on to this is, okay, well, first of all, is R countable? And probably before I do that, we should ask ourselves, was the irrationals countable? So we saw that W was countable. We saw that the integers were countable. And so how am I going to come up with a way of counting fractions? I mean, there's a lot of them, right? So there was this wonderful argument that they came up with, Cantor's diagonal. He was a German mathematician. And so what he did was he had the numbers. Here's the natural numbers on top. Here's the natural numbers on the bottom. And he wrote out a grid, and he just kind of walked his way through it. So, by doing that, here's 1, and so we'll map that to 1, and we follow down. Here's 2, 3, 4. We skip this one. 5, 6, 7, 8. So notice as I'm just walking through this, following a diagonal grid back and forth, I can actually count these fractions. So then to answer, Q is countable. Now you might ask me about the negatives. The same idea applies that we did with the integers. So we just alternate back and forth between them, and that's how we can also get around that. So yes, it's still countable. Okay, so is R countable? No. By doing so, what we've done is we've essentially gone from the discrete, which is kind of the counting world. So we've gone from, things where we have 2 and 3, 4. We have, like in the natural numbers, these large gaps where there's nothing that exists in between them, to which are countable. And now we've kind of filled in those gaps. I have 1, 2, 3, 4, and these are uncountable. And everything in there that we don't have with the rationals, we now have here. So about, maybe around here, square root of 2, and pi is around here. So that's what we've done. We've gone from a discrete world with lots of holes in between, and we've paved over these holes so that we can actually have a continuum of numbers. So again, we've seen now the idea of a limit, which is also very important in calculus. So we need to make sure that we have this idea of a limit getting closer and closer to something, and this will play a role later when we start to get into what we call derivatives and integrals. Okay, so now that we're working with the reals, why we have the reals, so that we have all these numbers to play with, we don't have to worry about things that don't exist. The nagging question is, are there other numbers outside of R? Okay, that's definitely not an open question. We'll eventually get to ask that, but we get to return to algebraic manipulations. So we were talking about addition, subtraction, multiplication, division. We can do that all within the real numbers. And not only that, we can also handle square roots and other functions as well with the real numbers. So we're going to start to do some more algebraic manipulation review. So the first thing I'm going to say is let's show that a plus b all squared is equal to a squared plus 2ab plus b squared. So the first thing I see over and over again, I should probably make this as a warning. A plus b, oh, even my pen won't let me write that. Does not, all right. It's not equal to a squared plus b squared. Okay. So I need to show that, and basically what I'm going to do is I'm going to expand. I'm going to do 2 copies of this. And then I can expand it. So I have a times a, so that's a squared. And then I have a times b, which is just ab. And the next part is I have ba. I'm just going to write it as ab. And lastly, I have b times b gives me b squared. Simplifying ab plus ab, that gives me 2ab, and I'm done. Okay. The next one is a squared minus b squared is equal to a plus b times a minus b. And this is what we call difference of squares. Because again, this is a square, this is a square, that's a subtraction or a difference. To show that, I'll start on the left-hand side, or sorry, the right-hand side here. So a plus b, a minus b, same idea. So I got a squared minus ab, a times b, and there's the minus. Then I have b times a with a plus, so plus ab. And lastly, I have a minus here, and b times b gives me b squared. So I have an ab plus an a minus ab plus an ab. So it leaves me with a squared minus b squared. Okay. They might ask you to expand. Here's a plus b cubed. Okay, so I can have, you could do it like this. And then do it. But what I'm going to do here is I have a plus b squared times a plus b. Okay, and I already have a formula, so I'm going to use that. I'm not redoing work that I've already done. I've already shown that's true. So a squared plus 2ab plus b squared. And same idea, just applying each of these. So now I have a cubed, and I have a squared times b, so there's plus a squared b. Then the next thing I have is so I have 2ab times a, so that's 2a squared b plus 2ab squared. Okay. And then lastly, oh, do I have another color? I don't know if this one has color. Oh, no, I have. There's one. There we go. Lastly, so AB squared, and then the last one is plus B cubed. Can I simplify this? I have a squared b plus 2a squared b. So yes, this can simplify right here. I have 3a squared b. So I've done that. I have 2ab squared plus ab squared. So that is 3ab squared. And I leave the b cubed. And there, I've successfully expanded a plus b cubed. Okay. Is there any patterns that I'm seeing? Well, it's very interesting though, as I'm expanding this. For the first one, I have a. The exponents here are decreasing. So in the first one, I have 3. In the second one, I have 2. I have 1, and then 0. And then I notice if I'm looking at the b's, there's no b's here, so maybe exponent is 0. I have b is 1 here, b is 2, b is 3. So I see, I see some patterns. But what are those coefficients there? So if we did something like expand a plus b all to the 6. Okay, that is getting really wild. I don't want to have to do all this expanding and algebra and collecting and so forth. So what I'm going to do is I'll start with like the same idea. I have a decreasing exponents as I'm progressing through my term. So I have a, and I'll start with, here is 3. So I'm going to start with a 6. A to the 5, a to the 4, a to the 3. Am I going to run out of room? Okay, maybe I might run out of room. I don't know. Same idea for the b's. There's no b at the beginning, but I'll have a b here, b squared, b cubed, b to the 4th, b to the 5th, b to the 6th. And then the question is what are those coefficients? Okay, so again, when we taught 106, you should have seen something what was called a binomial coefficient. Some other people would have seen it as just like choose notation. But the binomial coefficients, here I'll show you. That's from Pascal's triangle. Pascal's triangle starts with we start with 1, and then we have another row, and the way that we create the next row is by adding the two numbers above it. So 1 plus 2 gives me 3, 2 plus 1 gives me 3, and I just keep continuing this Pascal's triangle further. So I have 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and I still have 1. Oh, and we should have recognized by now Look at that. 1, 3, 3, 1. 1, 3, 3, 1. So that's for, there's row 3. And we've expanded it for the cubed of a binomial. Okay, well that just means that we should probably, if we were on row 3, we have 4, 5, and 6. Maybe we should get to row 6, and then those should be the coefficients for it. Same thing, 1 and 5 is 6, 5 and 10 is 15, 20, 15, 6, and 1. So again, I would write that as, at the beginning here is 1, here is 6, here is 15, here is 20, here is 15, 6, and the last one is 1. So this right here is Pascal's triangle. And what I've just illustrated in general is what we call the binomial theorem. So that if we have any to the n, that's just simply the summation of the terms. Okay, and this is what we've seen before in 106, so that is n choose k. So that's n factorial over n factorial times n minus k. But again, this is the theorem. You don't have to really memorize that formula if you can recreate it yourself without having to resort to using the formula. You can expand something using Pascal's triangle, and by using this idea, which is exactly what this is telling you, that you write out your first letter, A, and it's decreasing over the expansion, so from A to 6 to A to 0, and same thing, I start from B0 all the way up to B6. And then I just simply wrote in my binomial coefficients. So there it is. That's from row 6. Perfect. So again, if you didn't want to do that work, that expansion of a to the 6, a plus b to the 6, doing this, you know, distributing your terms, so forth, quick way. Okay, what's the next thing that we can do? We can factor. So we'll factor this, 2x squared plus 4x minus 6. What we can do is we can common factor that out, because I see that there's a common factor of 2. There's 2 here, there's a 2 in there, and there's a 2 in there as well. So the 2 comes out at the beginning. And so when I divide out by 2, I'm left with x squared plus 4 divided by 2 gives me 2x. Minus 6 divided by 2 gives me 3. I'm still not done yet. I can actually express those as binomials. So the way that I can do that is I use initialism or whatever. I usually write down MAN, M-A-N. So that's for multiply. They have to add, and then below that are the numbers. So I need to make sure that I can multiply from, that gives me the -3, so I need to be able to multiply out here, so that it needs to multiply to give me -3. I need to be able to add together to give me 2. And so I need numbers that multiply, two numbers that multiply together to give me -3 and add together to give me 2. So I could do 3 and 1, and then to make sure that I have the right signs, I'll give it minus there. So if I multiply them together 3 times -1, that gives me -3, and I add them together, 3 minus 1, that gives me 2. So that's good. So I have x plus 3 and x minus 1. For the next example, we have solve. (2x² plus 4x minus 6). I didn't do that by accident. That's on purpose because we've already done this work here. So I can actually factor that like this because we just did it. Okay, and this is equal to 0. So I need to figure out what x's give me 0. So the way I have, this has to equal to 0. So x equals -3, or x equals -1 equals 0. So that equals 1. Okay. Covered that. That goes out the way. Okay, so the next thing that we need to look at or recall is the quadratic formula. And on page 17 in the textbook, they give that. Okay, so what they say is, given a quadratic, which always has to have the form something, with x² in it. So it's, we'll use ax squared plus bx. Which textbook, sir? That is the textbook Calculus by Marsden and Weinstein, and it is posted on the Moodle website in our sections webpage. It's also readily available on Caltech's library webpage too. Okay, so this is a quadratic, and the formula for that is perfect. I'm glad I could answer that. The formula kind of goes, it's just x equals -b plus or minus the square root of b² minus 4ac all divided by 2a. What's more interesting about their theorem, they said if it's greater than 0, this radical here, or square root, if it's positive, which means that that's why I wrote it's greater than 0, so that's positive. Then there's 2 solutions, or 2 real. The other one is if it's it's equal to 0, so then there's 1 solution. And if it's less than 0, which means it's negative, there are no real solutions. They also give a name for this as well. They also call that the discriminant. So if they're asking, if there might be a question about the discriminant where they say if it's greater than 0, and then there's a quick question that you can ask about that. Let's just take a pause for a second and understand why I wrote no real solutions. So b squared minus 4ac, if it's less than 0, no real solutions. The reason for that is because when we were looking with the Greeks, they were looking at triangles. These rational numbers were positive. So sure, we could handle things like square root of 2, or we could handle minus square root of 2. But if this is less than 0, and again, I should have probably been a little bit more precise in this. I drew a circle around that, and really it should be around this right here. So this is called the discriminant. So I will use the blue to mean that I was writing for this. We can handle things like that. But the problem that we run into is if we run into things where we have like square root of minus 2. And that is not in the reals. So again, that comes back to our original question, which we had a little while ago. Are there other numbers outside of R? Of course. We have where the square root inside of it is a negative number. And that is something that is outside the scope of this course. But this is what we would call an imaginary number. And that is an element in what we call the complex numbers. I don't think I'll hold back. I mean, I'll tell you what complex numbers are. It's not something that we'll be running into. It's not, in this course at least. Complex numbers are any numbers a plus bi, where a is a real number, b can be a real number, and I is defined as the square root of minus 1. But again, these are the complex numbers are not something that we will be running into in this course. Okay, so we have the quadratic formula. Let's do that. So let's do an example. X squared minus 5x plus 3 equals 0. So just looking off of that, where we have ax squared plus bx plus c, I can tell you that from that, my a is equal to 1, my b is equal to minus 5, and my c is equal to 3. So again, I just substitute the values into the formula. So I have minus b, so minus b, which is minus 5, plus or minus the square root of b squared, so I'm minus 5 squared minus 4, I almost wrote down a, and a is 1 times c, which is 3, all over 2a. So simplifying that, I have minus 5, which is just 5, plus or minus. 5 squared is 25. I have minus 4 times, okay, so I have 4 times 3 is 12, so minus 12. All over 2. 25 minus 12 is 13. And I can also write that as 5 halves plus or minus square root of 13 over 2. Okay. So this was by solved by using the quadratic formula. Okay. I'll check the chat. I don't. Okay, good. So there's also another approach where it's called completing the square. It's not one of my favorite approaches, but it seems to be taught in this book as well. So completing the square. And I think that's around page 17 as well in the book. So completing the square. So if you're given the form ax squared plus bx plus c, they tell you that the first step then is to factor out the a. And then the second part is to add and subtract b over 2a squared. So that the final formula should look like ax squared plus bx plus c is equal to a all times, so a is times quantity, x plus b over 2a all squared plus c over a minus b over, b squared over 4a. Okay. So to do that, I'm going to do my example again. I'm going to use the same one that I used up here, which was x squared minus 5x plus 3. So again, solve. By completing the square. Okay. So I think what I did was there was no a to factor out because, again, here's my a and it's just 1. So a is equal to 1. So I've done step 1. And then the next thing that I have to do is add and subtract b over 2a all squared. So b over 2a all squared, well, in this case, b up top here is minus 5 over 2a. So again, a is just 1, so it's just 2 squared. Again, you could write that as 25 over 4. So what I can do now is it's telling me to add and subtract, this 5/2 squared. So again, I can kind of insert it to get plus 5/2 squared minus 5/2 squared plus 3. So you notice what I've done is I haven't changed anything essentially. From this step to this step, I've essentially added 0. So again, it's an algebraic manipulation technique that we're using. And because of the completing of the square, what I can actually do now is, since a is 1, I can just look at this part right here, and I notice now that I can rewrite this part right here, as this term right here, the x plus b over 2a all squared. So this then simplifies down to x plus 5/2 all squared, and then I'm left with the minus 5/2 squared plus 3, 0. So just on the side here, I have minus 5/2 plus 3. And so again, I can have 25ths over 4. It's a minus plus 3. And I'll write that over a common denominator. So to change the 3 into something with a 4 on the bottom, 3 times 4 gives me 12. And the minus 25 plus 12, that equals minus 13. So minus 13 fourths. Okay. So it's still left with x plus 5 halves squared minus 13 fourths. Then bringing the 13 fourths over to the right hand side, because I'm going to solve, I need to figure out what x is. Now I can solve this. I can bring the 13 fourths over to the right hand side, that becomes positive, and then I'm left with x plus 5 halves and squared. What I do now is I'm going to square root both sides. It becomes plus or minus on both sides. So taking take the square root. So now I'm left with plus or minus 13 over 4 and x plus 5 halves. And I'm almost done. I can bring the 5 halves over to the left hand side, so I get 5 halves plus or minus square root of 13 over 4, but that's also equal to, I can apply the square root on top and bottom of the fraction. So I have square root of 13 over square root of 4 is just 2. Oh, this is also okay. So just to kind of go over what we've finished then. In this lecture, what we ended up doing was we reviewed all of the number systems, starting with the naturals, the wholes, the integers, asking what is a countable. We did also what a quotient was. We proved that square root of 2 is something that is not in the rationals. It's actually irrational. And that the q's, while they're countable, the reals aren't. And that the reals are really a mixture, well, it's a combination of the rationals and the irrationals. These are the rationals which are countable, as well as the uncountable, the things that aren't included in it. And that's what makes R not countable. We got a little bit of exposure of what a limit was in this case, that we can actually get really close to something. For instance, using the rationals, we can get very close to an irrational number, but we can never actually touch it just using rational numbers. So again, that was something, the idea of a limit, that it's something you can get really close to, but can never touch it. And then I said that R is the set of all rationals along with the limit points of the rationals. Are there numbers outside of R? Yes, the complex numbers. And we ended up seeing that while we were doing some very straightforward algebraic manipulations. When we finally got to the quadratic formula, we introduced the idea of the radical, where actually b squared minus 4ac could be negative. And if that's the case, then that means that we actually have a negative number inside of the radical or the square root. And those are not allowed in the real numbers. We can have minus square root of 2 and the minus square root of 2. But having square root of minus 2 is something that is not in the reals. That is an imaginary number, which is part of the complex numbers. And again, that is a number set that's outside of the reals. It is outside of the scope of the course. But again, if you were dealing with quadratic equations, complex numbers pop up, then we can actually define from the reals, including the square root of minus 1, we can actually come up with a complex number. We did examples of the quadratic formula as well as completing the square. And I think that this is a good spot for me to stop for today. Is there any questions before we sign off? Do we have a quiz on Monday? No. We'll probably have a quiz on Tuesday. Next Tuesday. And we should be starting to do some assignments on that. We're going to do some questions based out of that, and I will post some of those questions that we have covered then in today's lecture. Now, again, there's a small caveat. That's for section 2. If you're in my class, that's Tuesdays when I have the quizzes. If you're in another section, section 1 or section 3, I can't really speak for the other instructors. It's their prerogative to decide on when they're going to give quizzes. But generally, I try to keep it on the same day, so it's at least easier for you to remember. Again, there could be other people from other sections that are watching this. Again, if I'm making any comments in terms of evaluation, it's pertaining only to section 2. It doesn't apply for your other sections. And the other thing too is, again, you'll end up making mistakes. It is practice. You will need to sit down. You need to sit down and write it out yourself. Even I make mistakes, and we make mistakes all the time. Sometimes we catch them, sometimes we don't. And I think probably one of the things that I remember, if you were watching Netflix recently, there was a Fran Lebowitz documentary that was done by Martin Scorsese. And, one of the things that struck me was she said something like that: you will continue to make mistakes. It's not like you only make mistakes until a certain age. You continue to make mistakes, and you have less of an excuse because it's very rare that you will have the opportunity when you're older to make a new mistake. So instead, you'll find, I can't believe I made the same mistake again. Again, practice your homework. You're going to make mistakes. I still make mistakes too. It becomes rarer and rarer, but I have less and less of an excuse as I've been doing it more and more. And I find I make the same mistakes. And for instance, this is something I see over and over and over again. A plus b all squared is not equal to a squared plus b squared. We spend a lot of time expanding, and then to see that very frustrating. So don't make that mistake. If there's any other questions, feel free to send me an email. You know my address. My email address, richard.kohar@rmc.ca. And the other thing I will do is I'll scan these after that I finish the finish the stream, and then I will post it on Moodle, so you'll be able to download this so you can see this chicken scratchy writing. You can add some of your own notes if you really need to, and you can start to work on some of the suggested problems from this section. Okay, thank you very much for tuning in. I'm Richard Kohar, signing off.